So today I thought we'd take another look at the design of the error correcting headphone amplifier that we looked at in the previous video. Now, what I'd hoped to do today was to make some distortion measurements that could finally prove once and for all whether or not it was a sensible idea. Now, that turns out to be trickier than I'd thought, and I've got some ideas about how I might approach that, but in the meantime, I have a cunning plan. What we'll do is we'll make some measurements of the output of the error amplifier itself. And from that, we should be able to infer some things about the behavior of the system as a whole. So let's give it a go. So we have the headphone amplifier powered up on the bench. The left channel input here is connected to the source output of our dynamic signal analyzer, and the main output here is connected to our audio analyzer. Now that's not really the main point of today's measurement though. The main point of today's measurement is pin 7 here, which is the error amplifier output of the op amp. And we're going to have a look at that in the time domain on the scope, and then we're going to have a look on the DSA, look at the harmonic content and see what we can learn from that. So we'll just set up the source, fixed sine at 1 kilohertz, source level 1 volts. And we see from the analyzer on the output of the headphone amplifier that we're getting around about 7 volts RMS, which is around about right, and that our THD plus N number is nothing stellar, to be honest. That's fine because our source isn't particularly clean, and that's not really particularly important. The main thing is just to check that we're not clipping, and that all looks good. Okay, so we've powered up the scope, and I've got it set to some 200 microseconds per division, 20 millivolts per division, and we're just going to probe the error amplifier output. There we go. And what we see is a combination of the 1 kilohertz tone, which is coming through, and some real high frequency stuff on top of that. That's something of a worry, and what I'll do is I'll change the time base and we'll just get some sense of the kind of frequencies we're dealing with there. Okay, so I'll change the time base to 50 nanoseconds per division, and I'll just probe pin 7 again, and that gives us a sense of what sort of high frequency content we're seeing there. And I gave a rough sort of ballpark estimate that we've got content something in the order of 5 megahertz there. Now, there's not a lot of it. It's not exactly oscillating, but it is a bit of a worry to see that content there, I guess. My thoughts as to the origin of this is that we have an op amp with a gain bandwidth of about 50 odd megahertz running with a closed loop gain of about 10 to 1, so we would expect the unity gain bandwidth to be about 5 megahertz. And I suspect that what we're seeing in the error amplifier here is more output as the gain of the main amplifier is starting to trail away. I'm a bit concerned stability wise. I don't like to see this kind of high frequency content. Now this is barely going to appear at the actual output. It's pretty tiny even at the error amplifier stage. So maybe not a huge cause for concern, but definitely a little bit of a worry. So now we're having a look at that signal in the frequency domain. We're looking at a 20 kilohertz span, and I'll just probe pin 7 and we'll have a look at our error signal. There we go. Okay, so what we see is mostly the 1 kilohertz fundamental, but we also see the second, third and fourth harmonics coming through there. What I'd really like to do is measure not so much the THD but the actual harmonic power, so let's do that. Special marker, harmonics, fundamental frequency is 1 kilohertz, and we want to know harmonic power. There we go. Okay, so what we're getting is about minus 68.5 dBV. Okay. Now, what I thought was an interesting test was to load down the output of the amplifier a bit. So right now that's running basically open circuit. So what I'm going to do is I'm going to put a 100 ohm resistor across the output. Now, running 7 volts RMS into 100 ohm load. Do the math, but something of the order of half a watt or so. That's rather a taxing load for a headphone amplifier, so we'll give that a go. So we've now loaded up the output. I can tell because that resistor's getting pretty toasty. Let's have a look. Now this is very different. So we see a whole bunch of harmonics in the error amplifier output, and we see that they are at a considerably higher level. So we're looking at minus 64 dBV. So we've jumped 4 or 5 dB there. Also interesting to sort of see that we've got the even harmonics, in fact, isn't it? Because there's not much second, but fourth. It's curious, isn't it? All right, fundamental 2, 3, 4, 5, 6, 7, 8. Curious. So at the end of all that, what have we learned? It does seem that our error correction circuit is at least helping, because we are seeing some harmonic content there, and we are seeing that if we load the output stage harder, that there's more harmonic content in the output of the error amplifier. So that does appear to be working. Now when we look at the levels involved, we see that we're looking at around about a millivolt odd of harmonic content at the output of the error amplifier, translates to around about 10 microvolts at the input of the main op amp, or around about 100 odd microvolts at the actual output. Relative to the kind of output level we've got there, we're looking at something around about 100 decibels down. That's not unreasonable, and that's certainly something that we should be able to measure with care. Obviously not with this sort of setup here with these unshielded cables, and it's all a bit dodgy, and we certainly need a much better source than the one we're using here. But it does look quite promising. Anyway, I hope that was enjoyable, and thanks for watching.